In low pressure hydrogen, there are no forces between the molecules except during collisions with each other. So essentially think of particles similarly in Brownian motion, but there are no forces acting between them. So that's just they're setting up a stage for the question they want to ask. Which statement will describe the motion of a molecule between one collision and the next? So let's bring our particles over here. All right. So it moves with changing speed and continuously changes direction. Okay, so between one collision and the other, let's say this red dot right here, which is now over here, which is now back here, is the particle. And it's gonna, like, because there's no forces acting on it, it's gonna keep going, what? In a straight line, right? In a straight line, and it won't accelerate, decelerate, and it won't turn, because there's nothing turning it. So as soon as it hits something, it's gonna hit it, then whatever energy it has, it's gonna bounce back. And between its second collision and the first collision, sure, it's gonna keep hitting different things and randomly move around, but between one collision and the next, it's gonna just move in a straight line with constant speed. So nothing's influencing its motion. So that only option is highlighted in D, and straight line. Correct answer is D. A wave on water travels towards the stationary boat. As the wave passes, the boat starts to move up and down and gains the kinetic energy from the wave. So wave has some energy and it gains that energy. Which property of the wave changes as the wave passes the boat? So what's going to happen is it has, like, let's say 100 energy, right? Some of that 100 energy is going to get transferred into the boat because it's going to move up and down. That's, let's say 20 of that 100 gets transferred, right? And you're left with a wave right over here, right? And that has 80 energy left, right? 80 schmeckles of energy, right? So what is changing about that wave? What's a more powerful wave? What's a high energy wave versus a low energy wave? The amplitude of the wave will change, because you can't change the frequency like that, right? The amplitude will change because it's losing that energy. The correct answer is A. Another way of thinking about it is, let's say, sound wave, right? As you go further and further away, the air kind of absorbs that energy a bit while the sound is propagating. So the loudness of the sound goes down once you're further and further away from the source, right? If some friend is shouting, he's right next to you, he's loud. But if he's 2 miles away, you can barely hear him. And if you notice his voice, it's the same voice. If you could have heard him, very little. Like it's not changing in frequency. It's definitely not going to change in speed, and the wavelength is constant because the frequency is constant. So the pitch isn't changing if it's losing energy, right? So you're familiar with waves losing energy, and amplitude is the only thing that gets lost when energy is lost by a wave. Or amplitude is reduced, that's a better way of saying it. Correct answer is A. The diagram shows a simple circuit. You have 2 lamps connected to a battery, a variable resistor, and a motor. What happens when the resistance of the variable resistor is increased? If this is going to get increased, the lamps are dimmer and the motor rotates more quickly. The lamps are dimmer and the motor rotates more slowly. So less power is going to all of them because this is taking the majority of the voltage. So everything's going to go down. The lamps have the same, okay, dimmer and more slowly. B is catering to our question. The manufacturer of an electrical heater states that only one heater must be connected to the main wiring through any fuse. Okay, so maybe it takes a lot of power, it takes a lot of current, and the fuse might, if you put 2 of them, the fuse might get, burnt out, will burn. The current in the circuit with only one heater is 9 ampere. All right, so if you have only one heater, it's 9 ampere. The fuse rating is at 10 ampere. Despite the warning, a second identical heater is added, as shown when the switch is closed to the fuse blows. The fuse is replaced with the 20 ampere fuse. Okay, so because you added 2 of them, and each will try to take 9 ampere, the wire is trying to carry 18 amperes, and now they've done something slightly smart. They've refused the fuse, replaced the fuse, refused the place, replace the fuse with a 20 ampere fuse. Great. What happens when the switch is closed? So when you turn it on, what's going to happen? Each heater only receives half the current. So nothing's stopping the current from flowing, right? It's the fuse will, if it crosses this amount, it will burn and prevent more current from flowing. So it's a safety precaution. So what you've essentially done is the rating, there was a reason why 10 amperes was put in here. Whoever put it here had an idea what the standard usage of was of this circuitry wherever this house is. Maybe other things are connected to it, or maybe there's a chance another things might connect to this. So he put it there 10 amperes for a reason. The current over here, the fuse is a safety device. What they're trying to say, under no circumstances should you use more than 10 amperes over here. That's why they put it. But you replaced it with a 20 ampere one. You just went like no you or something, right? So let's see what that damage that'll do. So the fuse won't blow up even though there's a lot more current going through now because it's higher rating. But there's something over here that might just, which we don't know about, might blow up. Let's see what major hazard can happen. Each heater only receives half the current. That's not going to happen because the circuit is this isn't, a fuse from Harry Potter. It's just going to continue working. It won't burn even the house if it catches fire. At 18 amperes, it won't blow. It'll allow current to flow, right? So each heater receives twice the current. That's again no, right? The circuit wiring connecting the heaters to the main may overheat. So yeah, that could happen because the wires, we think of them as like these supernatural things where like they can carry, all the current we want them to carry. But someone put a fuse here because they probably knew the current and the wires can probably carry at most 10 amperes or something close to that, 12 amperes. It probably has a rating on the wire. It's probably, just normal wire, not heavy duty wire, right? So think about it this, if you have a cell phone charging cable and you try to charge your laptop with the same cable, notice how thin it is, and laptops cables are much thicker. Do you think it'll be able to do it? For safety reasons, they prevent you from doing it, but it's going to heat up, it's going to blow, right? Catch fire or worse. Okay. So yeah, the wires may burn, may overheat, and may melt, right? So that's a risk. Nothing's going to happen to these two heaters because they're getting their 9 amperes unless there's a surge. That's a different story. I wonder if that's there. But at 20 amperes, the wire might take damage. Yeah. The fuse melts when the heaters are switched on. It won't cause the rating. The previous fuse would have, but this won't. Definitely. It'll let the house burn. So not a good idea to just randomly pick a fuse and put it in your house. You gotta know what the rating is of your system because this is a safety feature, right? It's another way of saying if the current exceeds this, rating for my circuit, turn that current off. That's the rating you pick for the fuse, essentially. And the correct answer is, the most likely answer is C. A coil is rotating in a magnetic field. The coil is connected to an oscilloscope, and the diagram shows the trace on the screen of the oscilloscope. All right. The coil is now speeds up. So it's essentially a turbine, right? Like your, dynamo or whatever you want to call it. You spin it faster. What's going to happen to the new trace? So what's the circuit? What's the current essentially in the thing? So So that was original. Now if it speeds up, obviously it's in a shorter time, it's completing one circle, right? So it should definitely do this, that it tries to, okay, let's try to do it like that. Something like that. It's doing it faster now, right? I hope that's faster. Barely looks faster, right? So it's trying to do it faster, but notice this, that you're adding more kinetic energy because the dynamo, the best way to think about it, now if you've ever played with like a, bicycles used to have, I wonder if they still do, they have dynamos. The faster you try to move it, the harder it gets. So you have to put more energy into it. And that's because what's happening is the more energy you put in, the more kinetic energy you try to give your generator or your dynamo or your turbine, the more of that energy tries to get converted into electrical energy. Let's go with EE, right? So that it gets really hard. So if you're increasing the energy, the electrical energy, not only the frequency is changing because you're spinning it faster, the electrical energy is also increasing because you're working harder. It's more kinetic, more faster, right? So all that energy is also being transferred to the magnetic, like it's not just making it faster, it's going to get real hard to move it fast. So it's kind of fun. You guys should kind of play with the dynamo. You'll understand what I'm trying to say. Anyway, so the amplitude will change as well, right? So because you're providing more energy, and the best way to look at it if you've never played with a dynamo is listen to what I'm saying, which is because essentially you're increasing the input energy. You're giving the kinetic energy, the rotor spinning because it has a motor attached, or someone's has a crankshaft and someone's manually doing it. They're giving it kinetic energy, which is turning into electric energy. If you increase this, the electrical energy should increase as well, right? And how would we see in the graph if that electrical energy is higher? The amplitude will be higher. Correct answer is B. A student balances a non-uniform object on a pivot. To do this, a weight is suspended near the left-hand side of the object as shown. Where is the center of mass of the object? This is a very straightforward question, I feel. So there's a force being acted on it over here because of the mass. There's a force. And because of this force, the pivot is over here and there's some distance. So it's causing a turning effect on this object, so to speak. Well, it is an object. So it's going to try to turn it which way? Counterclockwise. Counterclockwise, right? It's going to try to turn like that. Now, if you put, if the weight was over here, that weight would also produce a moment, right? That moment produced by the weight will also be counterclockwise, or CCW. So this won't stay balanced because you have to have a counter, or like counter for this counterclockwise moment, which is a clockwise moment. So it has to turn like that, the other way, right? We have to find a moment that's clockwise to balance it out, right? And we're not even getting to the right magnitude of it, right? So C will actually probably very likely not produce any moment because it's on the pivot. And why won't it? Because the weight is acting on it like that, so it won't cause any turning effect because it's not rotational anymore, right? If the weight was acting on the pivot, that would do what? Moment would be the force times D. The force is, well, for this case, is the weight times distance from the pivot, which is 0. So the moment is 0. Very cool equation when it works out that way. But this weight over here, if the weight is over here, and it kind of makes sense because it's bulging on this side, a lot more mass over here. So if the weight was over here and the pivot is over here on this side, this will create a clockwise moment. Only at D, if the center of mass is at D, will it create a clockwise moment. I think think I said counterclockwise a few seconds ago. Clockwise, which is required for this to take place. So D is our correct answer. Let's write that down. D. All right. A load L is suspended from two springs that are in parallel. The extension of the spring is X. Okay, so it's being expressed by X. So each of this spring is trying to carry this weight, right? It's trying to carry this weight. So let's talk about, let's say, spring A over here. Spring A, if I try to draw it, spring A is actually carrying half that load, right? Because it's in parallel and these two are both supporting it. Think about it this way. There are two people, you know, hanging from a cliff. The two people hanging from a cliff, or like three, and let's say there's like your friend, right? Sure. And he's trying to carry this guy who's fainted, right? And he's not that strong, but he'll find it a lot easier, won't he, if there was another guy also helping him? So he's carrying half the weight of this guy if his weight was L, right? He's carrying half that weight and this guy is carrying half this weight. So over here, only spring A, if we focus on just one spring or one guy, they're actually carrying half the weight, right? And with that much force or with that much load, this spring will extend by X. That's the extension of the spring. When this particular breed or kind of spring has this much weight, it'll extend by X, right? Now picture the same thing. What's going to happen is if you rearrange the springs again, let's say you go with white or blue this time around. Here's your cliff again, and here's your friend who was graciously trying to save, you know. But this time around, he's actually holding the other guy who's now carrying your unconscious friend. Why aren't you in the picture, dude? Like, dude, look at your friends. Anyway, your selfish acts aside, why is this arrangement different from this? Over here, they're sharing the weight. They're trying to carry it. But this guy, right now, this person over here has to carry the weight of the person, right? The weight of the person below him, this guy. Let's call him guy B, right? And that's guy A. And this was the load, right? So he has to carry B and the load, right? But the B has negligible mass because B is actually a spring, so we'll ignore B. So this person over here, which is turning white from the load, is trying to carry, is getting the full impact of the load. This time he's not sharing that load with anyone, right? That weight is not being shared. He's not getting any help in this arrangement. If anything, it's actually worse with this guy around, but we're ignoring his mass. And for the second guy, let's focus on him. For the second guy, it's the same thing. He's carrying all of this guy's weight as well, right? So both of these guys are under the same load, L, right? So what is the extension? Over here, these springs, let's just confirm, the extension of each spring is X, right? So when it was half the load, each spring was being extended by X, and that X, that extension of X, was not being added, right? Because they're in parallel, they're not like you know, it's not a chain, like one gets bigger, the other one gets bigger. So it's not like a chain reaction sort of thing. So the overall length is only increased by x over here. Over here, because the load is now double, let's go do some math on this corner. The load is actually double because you started with L over 2, now it's L. So each spring will extend by 2x, right? And because each spring has that weight, this spring will extend by 2x. And this spring also has the same load, right? Because he's still carrying the friend, also has an extension of 2x. A total extension can now be added because they're on top of each other. They're on top of each other, so this can be added, right? I mean, think about it. It's kind of common sense. And the total extension has to be 4x. And that's our answer. The answer is D. The list gives symbols of some physical quantities. You have acceleration, you have atmospheric pressure, you have density of water, and you have depth of water. Okay, which quantities from the list are used to calculate the total pressure at the bottom of a lake? So let's bring our lake in. Yay! All right, at the bottom of the lake, we have some detector that detects pressure, let's say, right? I mean, it does it. What do you mean, let's say? So the pressure being generated on this detector is the pressure caused by the water. So let's call that PW. And before that, the pressure exerted by the atmosphere. We'll call that PA. So this pressure is actually PA plus PW, pressure of the water, right? PA is, let's find it here, is pressure of the atmosphere. Okay, let's go with a different symbol because we're repeating it. And let's go with pressure of our gadget. So PG, okay, whatever. PG is equal to the atmospheric pressure, which is just P, and pressure by the water. But we don't know so the pressure of the, what do you call it? The atmosphere is constant, more or less, right? Because the height of the air above us is more or less constant throughout. So it's just one value, so it's more of a constant. But the lower you go, the heavier the water gets and the more pressure exerted by the water, right? I like to think of it as weight of the water, but it's more pressure because it's not one thing. Water will squeeze you from all sides. Okay, so this pressure you'll have to calculate to figure out the pressure of G right here. G, my man. All right, pressure of the water is going to be given by the density of the water, the gravitational acceleration, and the depth at its which. I like how depth is actually denoted by H. Everything is relative. Depth is just negative height, isn't it? Okay. So how many quantities are you using? You're using G, you're using P, you're using rho, you're using H, you're using all of them. So A is our best answer.